Okay, so this topic, atoms, elements and compounds, sees us build on the particle model that we looked at earlier in the year. And hopefully straight away what it does is it raises the question, what is an atom? So an atom is a very, very tiny object, unbelievably tiny. You would have to have about 1 million atoms all lined up in a row to be about the width of a human hair. So they're incredibly tiny. But crucially, everything that exists, or all matter that exists, anything that is made of stuff, is made of particles called atoms. Everything. Now, even though atoms are incredibly tiny, there are even smaller particles that make up atoms. And they're called subatomic particles. So often you see sub at the front of a word: submarine, submerge, subway. Sub basically means beneath. So the atom is made up of 3 subatomic particles. They are the proton, the electron, and the neutron. So this is a model of a sodium atom, and at its center what you can see is a cluster here of red and yellow particles, or red and cream particles, which I'll come to in a second. But that cluster is called the nucleus. Now, those different particles, the red and the cream particles, they are the protons and neutrons. Surrounding the nucleus, so going around in those circles, those blue dots there, they are the electrons. And then between the nucleus and the electrons is absolutely nothing. So in an atom, we have a central nucleus that contains protons and neutrons. Circling the nucleus are electrons, and then between the nucleus and the electrons is absolutely nothing. Now, I said the previous diagram was a representation of a sodium atom. So there are different types of atoms, and what makes them different is the number of protons. They can also have different neutrons, and they can have different numbers of electrons too. Now, in total, there are 118 different types of atom, and only about 92 of those occur naturally or exist in nature. So that means nearly every single thing in the entire universe is made from those 92 different types of atoms. Now, all of these atoms, all 118, they can be found on what is known as the periodic table of elements. You may have seen this or a table similar to this before, and the version I'm showing here lists nearly every single type of atom that exists. Now, I said already that all stuff, all matter is made up of atoms. And so one way we can think about atoms is like building blocks, like Lego bricks. And so just like with Lego bricks, you can join them together to make new structures. You can do exactly the same with atoms. Now, when they are joined together, we call that chemical bonding. Now, if you remember when we talked about or looked at particles, one of the things that we talked about was there being forces of attraction between the particles. And really, chemical bonding now is a little bit more detail. So in chemical bonding, those atoms, those particles, are stuck together very strongly, and those forces of attraction are very strong. Now, if they're attached together very strongly, that means you would have to put in a lot of energy to break them apart. So atoms that are chemically bonded together are very difficult to separate. Now, if something is made up of the same type of atom, then we call that an element. So this picture here, the fact that they're all orange, it's just to show that they're all the same type of atom. That would be an element. That is a pure substance that is made of only one type of atom, and that is an element. And actually, if you remember when we showed the periodic table, we said it was the periodic table of elements. So a periodic table of all of the different types of atom. But if you just focus on one element, then that element is made of only one type of atom. However, you can join together 2 different types of atom. Now, if that happens, we call it a compound. So a compound is when 2 or more atoms of different elements have chemically combined or chemically joined together. So all the elements that exist, all 118, can be found on the periodic table. And what you will not find on the periodic table is the name of any compounds, because what the periodic table only shows you are the elements, and elements are made of only one type of atom, whereas compounds involve atoms of two or more elements chemically combined or joined together. So, pause the video in a second, have a read of these questions, think of your answers, and then I'll talk you through the actual answers and hopefully you will have got them all correct. So, pause the video. Okay, so a substance is made of three different types of atom. Is it an element or a compound? Well, this is where we need to make sure that we understand our definitions. And our definition of an element is a substance made of only one type of atom. So if this is made of three types of atom, it cannot be an element, it must be a compound. Okay, the next one. A substance is made of three of the same type of atom. Is it an element or a compound? So let's remind ourselves about our definitions. An element is a substance made of only one type of atom. This tells us it's the same type of atom, so this is an element. What is the main difference between elements and compounds? So with elements, they're made of only one type of atom. Compounds are made of atoms of two or more elements chemically combined. What can elements and compounds have in common? So they're both made of atoms. And then finally, what are the names of the three subatomic particles? Well, they are proton, electron, and neutron. Okay, so here's another little exercise for you. There are 5 sentences below. 2 of them are true, 3 of them are false. I want you to pause the video and decide which are true, which 2 of them are true, and which 3 are false. So pause the video. Okay, so let's have a look at these questions. So if you want to know the name of a compound, you should look it up on the periodic table. Well, if we remember, the periodic table was called the periodic table of elements. So a periodic table only shows the elements that exist, only shows you the 118 different types of atom. So if you want to know the name of a compound, you should look it up on the periodic table. That is false. A lump of iron is an example of an element. So what we would need to do to be sure of that would be that we would need to look at our periodic table and see if iron is on there, which it is. And as the periodic table only shows the elements that exist, then that would tell us that iron was an element. So that is true. Table salt is made of sodium and chlorine atoms joined by chemical bonds and is therefore a compound. So a compound is a substance made of atoms of 2 or more elements. Sodium and chlorine are 2 elements. They are chemically combined. So yes, that is true. That is a compound. If you want to make an element, you need to take different types of atom and chemically bond them. Well, no, because an element is made of only one type of atom. And then finally, a piece of tellurium is an example of a compound. Again, we would need to look on our periodic table to know the answer for this for sure. Tellurium is an element. It is not a compound, so that is false. Now, all of those different types of atom, or all of those elements, the 118 of them, they all have a name and they all have a special symbol made of just 1 or 2 letters. The first letter will always be a capital and the second, if there is a second, will be lowercase. Now that symbol is universal, it's the same in every country. It allows science to communicate right around the world, and all of those symbols can be found on the periodic table. In fact, in a sense, you've already sort of seen them very briefly. But what we need to do is look at them now a little bit more closely. So if we find argon on the periodic table, we'll discover that it's represented with a 2-letter symbol, AR. And remember, the first letter is always a capital, and the second letter, if there is a second letter, will always be lowercase. So this is our chemical symbol for argon. Carbon has only 1 letter as its symbol, and of course this has to be a capital. So carbon's symbol is this capital C. The symbol for potassium is K. So one of the things to begin to realize now is that the symbol or letter isn't always the first letter of what we think of the name. So we might have expected potassium to have the symbol P or PO, but that's not the case. And one of the reasons is that the names for these elements have come about over, well, almost thousands of years, and the names can have different sources. So sometimes they're named after the place they were discovered, sometimes they're named after gods, sometimes they're named after their colour, and there is a whole variety of reasons as to why they got the name that they did. So you have to always make sure that you look at an actual periodic table to know for certain what symbol an element has. So for potassium, it's K. So copper, for example, or the symbol for Cu comes from the Latin name for Cyprus, which is where a lot of copper was mined during a particular part of history. So now we've looked at some chemical symbols. Now it's a chance or a time for you to test yourself. So you're going to need to have a periodic table to hand. You can look one up on the internet, or you might have one in a diary or planner or something. But I want you to now find and write the symbols for these different elements. And then press pause on the video, and then I'll reveal what the answers are. So there are the answers. Make sure that you've written capital letters where they should be capitals and lowercase letters where they should be lowercase. Make sure that you have actually written the correct symbol for each of those elements. Now the periodic table is a table, which means it has horizontal rows and it has vertical columns, and we give those rows a particular name. They're called periods, and we give the columns a particular name, and that's groups. And one of the things that you might notice is that at the top of many of the columns you've got a number, and so that's a group number. So that 1 refers to that column, and that's called group 1. That 2 refers to that column, and it's group 2. And then we have group 3, group 4, group 5, group 6, group 7, and rather perhaps confusingly, group 0. And some of those groups have special names. So group 1 is called the Alkali Metals. That's a group that you'll learn a lot more about later in your school life, particularly when you're doing the GCSE. Group 7 is called the halogens. And finally, group 0 is called the noble gases. Now, we've said already that we can think of atoms as building blocks, or I made the analogy with Lego. And if you think about Lego, you can have Lego almost in two forms. You can have it joined together, stuck together so that you get a structure. So the structure we have here is a wall, or you could just have all of the Lego bricks all sort of jumbled up, not stuck together. And we can have a similar view with atoms. Atoms can be stuck together, or they can just be simply jumbled together. And there is a difference between those two possibilities. Now, if they're stuck together, and if they're different types of atom, which is what our wall certainly looks like there, because we've got different types of Lego blocks, then you've got a compound. But if they're all jumbled up and you've got different types of atom, then what you've got is something called a mixture. So a mixture is when you've got more than one type of particle, and so we could be talking about an atom, but we could be talking about more than one type of compound, or we could be talking about a mixture of elements and compounds. But as long as they're not chemically joined together, we can think of them as separate or distinct particles, then we call that a mixture. And that's something we'll talk a lot more about later in our learning. So looking at elements a little more closely, they can be classified into two types, metals and non-metals. Now, about 3/4 of all the elements that exist are metals, and about 1/4 are non-metals. And generally speaking, the metals are arranged on the left-hand side of the periodic table and the non-metals on the right. But to see that more clearly, we need to just actually see a picture of the periodic table. So that makes it hopefully a little bit more clear. We've got almost like a staircase, and to the right of the staircase are the non-metals, and to the left of the staircase are all the metals. And roughly speaking, about 3/4 of elements are metals and about 1/4 are non-metals. So these are the elements that we did the symbols for before, but your task this time is to find them on the periodic table and to decide if they're a metal or a non-metal. So you'll need to look back at the previous slide, or copy the line that separates the metals from non-metals onto the periodic table that you have in front of you. So pause the video, find each of those elements that are listed and decide if they're a metal or a non-metal. So there you go, there are the answers. I hope you got them right. Maybe they should have been a little bit more jumbled up than that, but anyway. So metals and non-metals have quite different physical properties, and what we mean by a physical property is any characteristic of a substance. So that could be if it's coloured, if a characteristic could be conductivity, whether it can conduct heat or electricity. It could be its melting point and boiling point, i.e. they could be high or they could be low. It could be its strength, i.e. it's a strong material or it's not a strong material, and then finally whether it's magnetic or not. So these are all examples of physical properties. So thinking about melting points and boiling points, we can talk about them being high or low. But a sort of a useful rule of thumb is to think about what state of matter the substance is at room temperature. And typically if it's a solid, we would quite often say that therefore it had a high melting point because it hasn't melted by the at the temperature that it's reached at room temperature. Whereas if it was a gas, then we would definitely say it had a low boiling point because at room temperature it's already boiled. So let's look at the states of matter of the elements on the periodic table and see if we can see any pattern regarding melting point and boiling point. So everything in yellow is a solid, everything in green is a gas, anything in blue is liquid. There are only two elements that are liquid at room temperature. So we've got to remember these are at room temperature. If we think about where our dividing line was between non-metals and metals, we would see that it is here. So what we'd find is, with the exception of mercury, every metal is a solid at room temperature. Whereas when we look at non-metals, some are solid, but quite a few are gases. So there does seem to be a difference between the melting point / boiling point of metals and non-metals. So generally speaking, metals have high melting and boiling points, and non-metals have low melting and boiling points. But I must stress that's generally. That doesn't necessarily apply to every single example of a metal and every single example of a non-metal. For example, we saw that mercury was a liquid, and we saw with non-metals, silicon, carbon, they were solids. But as a guide or as a rule of thumb, metals have high melting points and boiling points, and non-metals have low melting and boiling points. When it comes to conducting electricity, there's generally quite a difference. So metals are good conductors of electricity, whereas non-metals are poor conductors of electricity. There are a couple of exceptions to that, but it's a good rule of thumb as at the moment. Now, if something's a poor conductor of electricity, then we say that it's a good insulator. Similarly, metals are good conductors of heat, whereas non-metals are poor conductors of heat. That should say heat, so that's a bit of a mistake. So let's just correct that. And similarly, if they're poor conductors of heat, we also again say that they are good insulators. Another difference is about how easily they can be shaped. So one of the features of metals, and a very important feature, is that they can be hammered into different shapes. That means that they are malleable. So that's probably a new word for you. But if you say something is malleable, you can say it can be easily shaped. So sometimes we talk about people having malleable personalities. Metals can also be stretched into wires. In that case, we use the word ductile. So if something can be stretched into wires, it's ductile. Now, non-metals are quite different. They're typically brittle, which means that if you hit them with a hammer or you try to stretch them, they would just shatter. So that's a very clear difference between non-metals and metals. As you probably already know or realise, metals are shiny, particularly when they're polished or they're cut. They can be shiny, and we say they're lustrous. Okay, so another word for shiny is sort of lustrous or luster. We can say something has luster. Whereas non-metals, again, generally speaking, do not reflect light well, and so they are typically quite dull materials. Now, dull here means that they don't really reflect the light. Finally, there are only 3 elements that are magnetic, but all 3 of them are metals. And the 3 elements that are magnetic are iron, nickel, and cobalt. There are no magnetic non-metals. You may realise or may know that steel is magnetic, but steel is actually a mixture or something called an alloy, and that's got mostly iron in it. So the reason that steel is magnetic is because of the iron that's in it. So we've looked at the periodic table, And now we need to look at types of substances. You could take this opportunity to maybe look at this periodic table and maybe try and recall as much as you can tell or as much as you know when you look at this periodic table now. So think about the names of particular groups, think about where the dividing line between non-metals and metals are, think about what those symbols represent, think about the differences between metals and non-metals. Just try and think of as much as you possibly can for when you see the periodic table. So the first type of structure we're going to look at or consider are molecules. So if you have, and this is an approximate number, but if you have between 2 and 100 atoms chemically bonded together, then we call that substance a molecule. And they can be either the same atoms or they can be different ones. So for example, the blue could, each one of those blue atoms could be hydrogen. And so the molecule there that we've actually got is H2. If we look at the one on the right, it could be that the orange is carbon and the sort of, I don't know, reddy are oxygen. And so what we would actually have there is the molecule carbon dioxide or CO2. Okay, so I'm actually going to label the atoms in this molecular substance here because I think that will actually help us understand a little better what we're considering here. So each one of those red atoms is an oxygen, and each one of those white atoms is a hydrogen. So have a think about what substance you think this might be. So you may have realized that what we're looking at here is H2O. So one of the things to say is that you can have many molecules of the same substance, and this is a little bit like, this is now, an extension of our particle model. So each one of these molecules is a particle. So inside the particle we have an oxygen chemically combined with two hydrogens, and then between the particles, well, we just have very weak forces of attraction. Here's just a slightly different sort of view of it. So those water molecules, they are made of atoms that are chemically combined, and then each of those molecules are separate from each other. So they are not chemically bonded to each other. They are like separate particles. Now, to know whether a substance is molecular or not, or if it's made of molecules or not, there is a way of using the chemical formula. It's almost perfect. It will almost always works. And for the moment, it's absolutely fine. But we can use the chemical formula if we've been given it to work out whether something is a molecular substance or not. So basically, it's a flow diagram of questions. So our first question, or what we're trying to answer ultimately, is the substance made up of molecules, or in other words, is it molecular? So the very first question we have to ask ourselves is, when we look at the formula, does it contain non-metals only? So we need to understand where the non-metals are on the periodic table, where the metals are. So you can see how our knowledge is sort of building on top of itself. Now, if the answer is no, so if there is at least one type of metal in our substance and the answer is no, then straight away we know it's not made of molecules. If the answer is yes, we go to the next question. So we haven't yet proved or shown that it's made of molecules, but we at least are on the way to that still being a possibility. Then we've got two questions. Is it made of more than one non-metal? And then does it have a subscript number in its formula? Now, subscript is the small number that we see in the formula. Subscript, again, there's that word sub that we spoke about earlier. It means beneath. So subscript is basically beneath the line or beneath the writing. So if we have one of those small numbers that we see, look, there's our example at the bottom there. So if we answer yes to either of those questions, or both, then if we answer yes, then the substance we're looking at is molecular. So let's see how we got to hydrogen, H2. So is it made of non-metals only? Well, The only element in it is hydrogen. That is a non-metal, so the answer is yes. Is it made of more than one non-metal? No, it's just hydrogen, so there's a no to that, but we've still got to ask the second question. Does it have a subscript number in its formula? So we can see that little small 2 there, so the answer is yes to that. So we only have to answer yes to one of these questions, and then that tells us it's molecular. If I look at HF, that's made of hydrogen and fluorine. Hydrogen and fluorine are both non-metals. We would look at our periodic table to know that. So we answer yes. So that takes us to the next questions. Is it made of more than one non-metal? Well, hydrogen and fluorine. So the answer is yes to that. So we can just straight away go to proceed, and yes, it's molecular. Does it have a subscript number in its formula? The answer is no, but because we were able to answer yes to the first one, that was enough. Finally, C6H12O6, which is glucose. Is it made of non-metals only? Well, carbon, hydrogen, and oxygen are all non-metals, so it is non-metals only, so we go yes. Is it made of more than one non-metal? Yes, because we've got carbon, hydrogen, and oxygen. Does it have subscript numbers in its formula? 6, 12, 6, absolutely. So we have said yes to both of those questions. We only needed to say yes to one. So yes, it's molecular. If we just look at an example here in the bottom left, let's just take C, which is carbon. Is it made of non-metals only? Yes, it is. So that takes us to the next question. Is it made of more than one non-metal? Well, no, because it's just carbon. And does it have a subscript number in its formula? Well, you're going to have to believe me that that is the formula for carbon that we would use. So there is no subscript number. So the answer at that point is no. So we can still say what it's got. We can say it's got a giant covalent structure, and that will mean more to us later. But what it isn't, is molecular. So I would just like you to do all of the symbol. I shouldn't have put as many different substances as I have here. So I just want you to do the symbol one. So all the way from oxygen, or from O2, all the way to NH3, which is ammonia. And I want you to decide whether it's made of molecules or not. You're going to have to look at the previous slide, I'm afraid. So you might have to flick backwards and forwards a little bit on the video. But one of the things that you could do is you could just copy the formulae out onto a piece of paper, and then go back to the previous slide on the video, and then try and work out whether it's made of molecules or not. But yeah, basically, if you can pause the video now, and then we'll look at the answers in a second. Okay, so let's look at O2 first. Is it made of non-metals only? Yes, because it's just oxygen. Is it made of more than one non-metal? No. But does it have a subscript number in its formula? Yes, it does. It has the 2, so in the O2. So yes, it's made of molecules. CO2. Is it made of non-metals only? Carbon and oxygen are both non-metals, so yes. Does it have more than one non-metal? Yes, carbon and oxygen, so it is a molecule. But just to confirm, it also has a subscript number in its formula, so that is also yes. Okay, Ki is potassium iodide. So does it have non-metals only? Well, potassium is a metal, so straight away we can say no to that. Magnesium chloride, MgCl2. Does it consist of, or is it made of non-metals only? Well, magnesium is a metal, so the answer to that is no. C60, is it made of non-metals only? Yes, it's just carbon. Is it made of more than one non-metal? No, because it's just carbon. However, we still got to ask the second question, does it have a subscript number in its formula? And the answer is yes. Fe, okay, so that's iron. Is it made of non-metals only? No, because iron is a metal. HBr, is it made of non-metals only? Well, we've got hydrogen and bromine. They are both non-metals, so we can go to the next set of questions. Does it have more than one non-metal in its formula? Yes, it does. It's got hydrogen and bromine. So straight away we can say that's made of molecules. C10H22O. So is that made of non-metals only? Well, it's made of the elements carbon, hydrogen and oxygen, and they are all non-metals, so yes. Is it made of more than one non-metal? Yes, because it's carbon, hydrogen and oxygen, and it has subscript numbers, so it's definitely a molecule. Al2O3 or aluminium oxide. Is it made of non-metals only? Well, aluminium is a metal, so the answer straight away to that is no. And then lastly, NH3, which is ammonia. Is it made of non-metals only? Well, it's nitrogen and hydrogen, so they are both non-metals, so yes. Is it made of more than one non-metal? Yes, because it's nitrogen and hydrogen, and it also has a subscript number, so that is definitely made of molecules. So this is probably beginning to become apparent anyway, but one of the things that we're looking at or considering when we look at the chemical formula of a molecular substance, and we know whether something is a molecular substance, i.e. it's made of molecules based on the flowchart we've just been using, that formula tells you which atoms and how many of them are present in each molecule. So if we look at some examples here, if I just do the first one, we've got hydrogen, and it has the chemical formula H2, and it asks us which atoms are present, and it's also asking us how many of them there are. So there are that little subscript refers to the element just before it, so that little 2 refers to the hydrogen, so there are 2 hydrogens or 2 times hydrogen. Is it an element or a compound? Well, it's only one type of atom. It's only hydrogen, so that is an element. So would you just like to have a go at the remaining substances and pause the video, and then we can have a look at the answers. Okay, so we've got oxygen. Its formula is O2. That little 2 tells us there are 2 oxygen atoms in the molecule. And it is made of only one type of atom, so that is an element. We've got nitrogen, N2. So again, it's only nitrogen atoms. There are 2 of them, and it is an element again because it's only one type of atom. Then we've got H2O, which is water. So we've got to think about how the formula works here. So we've got that little 2, and it comes after the hydrogen. So that's telling us there are 2 hydrogens, and then the oxygen doesn't have a number. So if it doesn't have a number, that means 1 times. So we've got 2 times hydrogens and 1 times oxygen. And that chemical formula tells us that we've got more than one type of atom. Because it's a molecule, it means they're chemically combined. So that is a compound. And we've got methane. So methane is natural gas. If you've got a gas cooker, this is the fuel in your gas cooker. If you've used a Bunsen burner, this is the fuel in a Bunsen burner. So we've got 2 elements. We've got carbon and we've got hydrogen. There is no number after the C, so that tells us there's 1 carbon. And there's a number 4 after the hydrogen, so that tells us there are 4 hydrogens. So we've got 1 times carbon and 4 times hydrogens, and again they're chemically combined. They're different types of atom, so that is a compound. And then finally CO2. So there is no number after the C, so that means there's 1 carbon. There is a subscript 2 after the oxygen, after the O, so that tells us there are 2 oxygens, so that is 1 times carbon and 2 times oxygen, and that is also a compound. So one other thing to say, sorry about this table, is that not only was this about what does the formula tell us about how many atoms and so on, those particular formulae that have been chosen, so hydrogen, oxygen, nitrogen, water, methane, carbon dioxide, those formulae are important formulae. So they are formulae to remember. So one thing to take away from this slide is to remember those particular formulae. So this is just another way of representing molecules. So we've got a little key there. So we're told that every circle which is just unshaded represents a hydrogen. Every circle that's got that sort of cross-hatching is oxygen. and every circle that is solid black is carbon. So if we think about what we've got in each of these boxes, if we start with this box here, so one thing to say is this is one molecule and this is a second molecule, and they are clearly the same type of molecule. So let's think about what each one of those molecules actually consists of. So we've got one of the black circles at the center, so that's a carbon, and then we've got 4 white circles joined to it, so they're chemically joined. This is a compound, and each one of those white circles is a hydrogen. So each one of these molecules is made of carbon and hydrogen. It's made of 1 carbon and 4 hydrogens. So the chemical formula for this substance would be CH4. If we look at the next one here, we've got 3 of the same molecule. So if we just focus on one of them, we've got 1 oxygen atom, and attached to that are 2 hydrogen atoms. So if we were giving the formula for this, it would be H2O. Okay, so 2 hydrogens, 1 oxygen. If we look at the next one, we've got 3 of the same molecule. Each one of those, each molecule has 2 hydrogen atoms. So that is the representation of the formula H2. Then in the bottom left, we've got 2 of the same molecule. They are 2 oxygen atoms, so the formula is O2. And then lastly, we've got, again, 2 of the same molecule. It's a carbon with 2 oxygens attached to it, so that would be CO2. Okay, so we've got a little challenging exercise now. So it's going to ask us to draw our own diagrams. So I want you to have a go at this before I talk you through. Just have a go. So we've got a mixture of hydrogen molecules and oxygen molecules. We've got to have a mixture of oxygen molecules and water, a mixture of 4 molecular substances, a mixture of elements, and a mixture of compounds. So I think we can make these up using the compounds that we looked at on the previous slide. So if we have a circle which is white inside, that is going to equal hydrogen. If we're going to have a circle which is solid black in the center, then that's going to equal carbon. And then if we have a circle and it's grey in the center, then that is going to be oxygen. So you should be able to do this hopefully with a pencil. So you might have to look back, look at the different substances, the methane, hydrogen, oxygen, water, and so on. And on the following slide of this, I'm going to have 5 boxes, so I'm going to be able to draw my diagrams for these. So you want a box basically for each one of these, and then in each box you want to satisfy what this is asking you to do. So in the first box you want a mixture of hydrogen molecules and oxygen molecules. Second one, a mixture of oxygen molecules and water, and so on. Okay, so on a piece of paper, have a go at that, and then I'll go on to the next slide. You pause the video, I'll go on to the next slide, and then I'll draw my versions of these. Okay, so starting with the top left-hand box, I've got to do a mixture of hydrogen and oxygen. So I know that hydrogen is H2, and I said that circles with a white center were hydrogen. So I'll put a couple of those in. And then oxygen was also 2 atoms stuck together, so 2 oxygen atoms stuck together, but what I need to remember is I represented oxygen by having them coloured in grey in the centre, and I'll put a couple of those in. So I've got more than one type of particle, I've got more than one type of molecule in my box that aren't chemically joined together, so that's one type of particle. That's the second, so that means I've got a mixture, and I've got a mixture of hydrogen and oxygen. Okay, on the next one it says a mixture of oxygen and water. So I'm going to draw my oxygens first. So again, it's O2. So I need to have them joined together. I need to make sure that it's clear that they're oxygen. I said they were going to be, that they were sort of grey in the middle. So they're my two O2 molecules. And then water is H2O. So that's an O in the middle and then a hydrogen attached. I'll draw another one, O in the middle and a hydrogen attached. And I've just got to make sure it's clear that it's an oxygen in the middle by colouring it in with the, to make sure it's clear it's oxygen in the centre. So I've got two oxygen molecules, two water molecules. So I have a mixture of oxygen and water. Now I've got a mixture of 4 molecular substances. So I'm going to do methane for this. So methane was CH4. So I have a carbon at the centre. So I can colour that black because that was in my key. Then I have 4 oxygens attached to it. So that's 1 molecular substance. I could have carbon dioxide. So that was carbon in the middle, which is black. And then dioxide means there's 2 oxygens. I have to remember I'm representing oxygen with this grey in the middle. And then I need 2 more molecular substances. Well, I may as well do water and, I can do water. Sorry, I'll do water and hydrogen. So water is H2O. So I've got 3 atoms and the central atom is the oxygen one. So I have to colour that grey. And the 2 joined onto it hydrogens, which are just white. And then I'll have 2 hydrogens. So I've got 4 molecular substances: methane, CH4, carbon dioxide, CO2, water, H2O, and hydrogen, H2, and they are separate from each other, so that tells me they're a mixture. Then a mixture of elements, well, to be honest, I could just simply do the first box again, because I have in the first box, I have hydrogen and I have oxygen, so they're both elements, and they are a mixture because they're not chemically combined together. So I'll just do 2 hydrogens and then 2 oxygens. I'm going to make it clear that they're oxygen by filling them in with the grey to show that they are oxygens, because that was in my key. Okay, so there's my mixture of elements. And then mixture of compounds. Well, so I've just got to make sure I have only compounds. So I'll do methane and carbon dioxide. So I'll do 2 methanes. So I've got to remember that's CH4 and the centre is the carbon. And then the 4 atoms that attached are hydrogens. Do another one. Okay, so there's my second CH4. And then I'll do carbon dioxide. So that's carbon in the centre and 2 oxygens attached. So I have to fill in that central one black because that's what I do for carbon on this key. My oxygens are the grey. And then I'll do another CO2. And there we go. So you could have done slightly different versions of these, but what's important on each of them is that, well, this was very clear. It had to be, you had to have at least 1 hydrogen molecule and at least 1 oxygen molecule. On the second, you had to have at least 1 oxygen molecule and at least 1 water molecule. Third one, as long as it was 4 different molecular substances, it didn't matter what they were. Mixture of elements, well, again, you could have had different types, but you would have needed to have a key to show which atom was which. So I've just done hydrogen and oxygen again. And then a mixture of compounds, so that each one of the particles has to be more than 1 type of atom. So I've gone for methane and I've gone for carbon dioxide. So air is actually a mixture of different substances. So we've got like a pie chart here, and you can see that nearly 4/5 of air is nitrogen. And we know that nitrogen is N2. Nearly just over a fifth of air is oxygen, so we know that's O2. And then the remainder, which is a very small amount, less than 1%, is the element argon, the element xenon, the element neon, the element hydrogen, the element helium, the element krypton, and then finally the compound carbon dioxide. So we could actually put all the symbols for those too. So argon would just be AR, xenon would be just Xe, neon is Ne, hydrogen we know is H2, helium would be just He, krypton would be just Kr, sorry, and then carbon dioxide we know now is CO2. So air is a mixture of elements and compounds. Okay, so as we saw, air is a mixture of molecules, although it does have some single atoms. So if you looked at those noble gases, if you looked at argon, xenon, neon, krypton, helium, they're all in group 0 of the periodic table, and they're all noble gases. They actually exist as just single atoms. But if we think that air is mostly nitrogen and oxygen, then we can think of it as a mixture of molecules. And then, so it's asking us here to draw a diagram like the ones that we've done already, but this time we're going to represent air, and we've got to represent it proportionally. So we've got to have 8 molecules of nitrogen to 2 molecules of oxygen. So let's have a key. So with oxygen, we did oxygen to be the grayed out particle, and what we'll have for nitrogen is we'll use blue. So nitrogen is going to be the blue particle, and so what we need to do is we need to draw our box. Not brilliantly drawn here, you can do a better job than me. And so you need to draw now, or you need to draw a box like that, and you need to fill it with 8 molecules of nitrogen and 2 of oxygen. If you can't remember how many atoms are in nitrogen, maybe you should look back in the video a little bit earlier to where we looked at the different formulae and looked at how many atoms of each element were in those formulae, maybe just to remind yourself. But pause the video and then have a look at the answer. So there we go. We've got 1, 2, 3, 4, 5, 6, 7, 8 molecules of nitrogen, because nitrogen is N2, and then 1, 2 molecules of oxygen. So how can you know, or how could you know whether the formula of an element was something 2 or not? If you think about it, we've heard about N2, we've heard for nitrogen, we've heard about O2 for oxygen, and H2 for hydrogen. Well, there is something pretty useful, and that is the fact that any elements whose name ends in gen, or if you remember what the name of group 7 was, it was the halogens, so that's got gen in it, but of course it's a group name, then they exist as pairs of atoms. So we've got hydrogen, we've got nitrogen, we've got oxygen, and then the halogens, the ones that we're mostly interested in, are fluorine, chlorine, bromine, and iodine. So that's group 7. So they're halogens, which is group 7 on the periodic table. So all of those elements will exist as pairs of atoms. So we've got H2, N2, O2, F2, Cl2, Br2, and I2. This honestly is a really, really, really useful thing to remember for the rest of your schooling, because it will help prevent you from making mistakes when you're doing your GCSE chemistry and even A-level chemistry. Okay, so we've looked at non-metals, so now we should look at metals. So let's just, ask the question, is iron made up of molecules? And when we look at the first question, it says, is it made of non-metals only? Well, iron is a metal, so the answer to that is straight away no. So at the moment, all that tells us is that it isn't molecular. So if it isn't molecular, what is it? So that's what we're going to consider now. Like, what is the structure of substances that are not made up of molecules? So substances like iron, substances like sodium chloride. So we're going to call these structures giant structures, and we'll understand a bit better why we're calling them giant structures in a bit. But one thing to say is that if we had a kilogram of iron, we would have 1.1 times 10 to the 25 atoms. That is an incredibly large number. That is more seconds than in the history of the universe. So this gives you a better sense, maybe. We can see just how many atoms that really is. So like I say, that's more atoms than there are seconds in the history of the universe. It's an enormous number. And when we're talking about a giant structure, we're thinking visually of something like this. And this is only a very, very tiny part of it. So you've got these arrows coming off at the side. And what we're trying to say is what you're seeing here goes on and on and on and on and on and on. And it would also be going on and on and on upwards as well. So they are just atom after atom after atom after atom after atom and so on, which is why they're called giant structures. Now, they are chemically bonded. There are billions and billions of them. In fact, billions is just too small a number. And again, just reminding ourselves that what we're looking at here is something that we can consider, something we can think of as being a giant structure. This is totally different than those molecules that we were looking at earlier, where it was just 3 atoms stuck together or 4 or 5 atoms stuck together. In fact, if you remember right at the beginning of molecules, we said, and it was just a guide, if there were 2 to 100 atoms stuck together, it was a molecule. Here, we're talking about billions and billions of atoms stuck together. Now, giant structures can be elements or they can be compounds. So on the left, we've just got one type of atom, and we're just using that atom to represent iron. And on the right, we've got 2 types of atom. We can clearly see they're bonded or chemically combined. So, and this is just a representation of iron oxide. But even though one's an element and one's a compound, in these 2 examples, they are both giant structures. So in making that comparison with molecules, we've got 2 to 100 atoms joined together. Giant substances, we've got billions of atoms joined together. But molecular substances can be elements or compounds, and giant substances can be elements or compounds. So what does it mean when we come to do formulae? Well, we can still write formulae for giant structures just like we could for molecules. So we could write the formula for water and say it was H2O, and we can write the formula for something like aluminium oxide as Al2O3. Now, the difference is that if we know for sure it's a molecular substance, then we can say in H2O that there are 2 hydrogen atoms and 1 oxygen, and they are atoms joined together to form 1 molecule of water. But it is a little bit different for something like aluminium oxide here. What we're actually learning from that formula are the proportions or the ratios of atoms. So it's not saying there are only 2 aluminium atoms and 3 oxygen atoms. What they're saying is that for every 2 aluminium atoms, there are 3 oxygen atoms. So they are ratios rather than exact amounts. So have a look at our iron oxide again. And what we're trying to do with the formula is to work out essentially the ratio of the iron to oxygen atoms. When we do the ratio, we do the simplest ratio. So we sort of divide it through so that we get the simplest numbers. So I'd like you to have a think about what you think the ratio of iron to oxygen atoms is in this diagram, and then have a think of what you think the formula might be. So pause the video, have a think. Okay, so one thing we could do is we could count them all up, but I think what we've got is if we look at every, let's say the white is the iron, so if we look at every iron atom, surrounding it are 4 oxygen atoms. So there's an iron atom, and then 1, 2, 3, 4. And if we look at every oxygen atom, so that we look at, say, this oxygen atom, surrounding that is 4 iron atoms. So every iron has 4 oxygens surrounding it, every oxygen has 4 ions surrounding it. So that suggests to me that for every 1 iron there is 1 oxygen. That is the ratio, a 1-to-1 ratio. And so if we were writing the formula for iron oxide, we would have FeO. So we don't have a number after them because we're saying if we don't have a number here, that means there's just 1. And there's no number here, so there's just 1. So this is a 1-to-1 ratio. So I'll just do that. So it's a 1-to-1 ratio. And that's of iron to oxygen atoms. So now we've got some other substances which are not molecular but are giant structures. So for each of them, what I'd like you to do is say what atoms the substance contains or what elements the substance contains and in what proportion. So the first one's been done for that calcium carbonate, so that's CaCO3. For every one calcium, there's one carbon and 3 oxygens. So pause the video, have a go at the ones that follow, and then we'll look at the answers together. Okay, let's look at the first, which is NaBr. That's called sodium bromide. If we look after the sodium, there's no number, so that means there is 1 times sodium. And then I'm going to use this to do the ratio. And after the bromine, there is no number, so it's 1 times bromine. So for every 1 sodium atom, there's 1 bromine atom. If we look at CuCl2, which is copper chloride, there's no number after the copper, so it's 1 copper. And then the proportion then is there is a little 2, a subscript 2 after the chlorine, so there are 2 times the chlorine atoms. Aluminium oxide, there's a little 2 after aluminium, so that's 2 times aluminium. And then there is 3 times oxygen. So that's the ratio, 2 to 3, 2 aluminiums every 3 oxygens. Then we've got barium. So there's no number after the barium. So it's 1 times barium. And then the proportion, there's no number after sulfur. So 1 times sulfur. And then there's a little 4, subscript 4 after oxygen. So 4 times oxygens. Iron chloride is next, FeCl3. So no number after the iron, so 1 times Fe, and then there's a little 3 after the chlorine, so 3 times Cl. So for every 1 iron atom, there are 3 chlorine atoms. Then we've got lithium nitrate, so you wouldn't necessarily know that was how you said the name for that compound. That is something you'll learn in year 8, or possibly actually towards the end of year 7. So we've got no number after the lithium, so 1 times Li. There's no number after nitrogen, so 1 times N. And then there's a little 3 after the oxygen, so 3 times O. So for every 1 lithium, there's 1 nitrogen and 3 oxygens. And then finally, we've got KOH, which is potassium hydroxide. No number after the potassium, so 1 of the potassium. No number after the oxygen, and no number after the hydrogen. And those are our proportions, our ratios of each of the elements in those substances. So this is a sort of a little summary exercise. So again, what I would like you to do is you could always label each box on the left-hand side A, B, C, D, or you could do it's 1, 2, 3, 4, 5, whatever, and then you could label the boxes on the right A, B, C, D, E, and so on, and then you could match the number with the letter. But I will try to draw lines. So if you want to pause the video, have a think about which part of the right-hand side goes with the left-hand side. So atoms are made of, and then choose which part of the right-hand side would complete that sentence. So basically how the right completes the sentence on the left. That wasn't very well described, but hopefully it makes enough sense. So pause the video and have a go. Okay, so atoms are made of protons, neutrons, and electrons. Okay, atoms can be joined together by chemical bonds. When a small group of atoms are joined together, we call this a molecule. A substance made of lots of molecules is a molecular substance. A substance made of billions of atoms all joined together is a giant substance. Molecular and giant substances can be elements or compounds. And the chemical formula of a substance tells you how many atoms are in that substance and what those atoms are. So we're just going to finish with just some little exercises. It's talking here about the diagram on the right shows a molecule made of 3 atoms. You can see what those atoms are. So which chemical formula should be used to represent the molecule? So I want you to decide between A, B, and C, and D. So pause the video, have a think, make a selection, and then I'll tell you what the correct answer is. So the correct answer is C. So one thing, the reason the others are wrong is when we're giving a formula, we would collect together all of the same type of atom. So we wouldn't do OSO. we would just have O once and then say how many oxygens there were. In this case, there are 2. The reason B is wrong is that whenever we're saying how many of an atom there are, it's always a subscript number. So it means it has to be below the line, not above it. And then D is just wrong because it's counted the number of atoms incorrectly. So this one has got a key, all right? So it's telling you what each type of atom is in these substances on the left. And what you've got to do is you've got to pair up these substances on the left with the correct formula on the right. So if you want to pause the video and make your choice, so maybe call these 1, 2, 3, 4, and then decide which formula matches 1, 2, 3, and 4. And then, yeah, just pause the video and then we'll look at the answers. Okay, so in this one, we've got 1 carbon and we've got 4 oxygens joined to it. So that's CH4. With the next one, we've got 2 carbons. So these are all joined together, all chemically bound. They're all stuck together. So 2 carbons and 1, 2, 3, 4, 5, 6 hydrogens. So that is going to be C2H6. The next one, we've got 1 oxygen atom and 2 hydrogen atoms. So that is H2O. And then lastly, we have got 2 oxygen atoms, 2 hydrogen atoms. So although this, so now we've got a choice, but if we remember, we collected together the atoms of each element and then said how many they were using a subscript number if there was more than 1. So our formula here is H2O2. And this is our final bit. So we're being told we've got a jar containing white crystals and it's labelled NaCl. And NaCl is the chemical formula for sodium chloride. And so we need to select the diagram that best represents this formula. So if we look at what our options are, we've got 1 sodium and 1 chlorine. Now that looks like a molecule. So what we would have to decide is sodium chloride, is it a molecular substance? Is it made up of molecules? This is a funny one. I mean, that really, I have to say, I don't think there's any real logic. I mean, it looks like a collection of molecules. So, I mean, I suppose that's a possibility. Again, if we thought that this was a molecular substance, and while we haven't seen a sort of 3D picture like that, if we just looked at one side, that would just basically look a lot like the giant structures that we were looking at earlier. So we would have to decide if it was a giant structure or not. So we have to think about sodium chloride, and the first thing is it's NaCl, right? That's the formula. And the first question to decide whether it's made of molecules or if it's molecular or not was, is it made of non-metals only? And when we look at the periodic table, we know straight away that sodium is a metal. So we cannot say it's made of non-metals only. So it cannot be molecular. So it cannot be A, it cannot be B. If it's not molecular, then it's a giant structure, and so it has to be C. So that finishes this topic, atoms, elements, and compounds. If you've got any queries about anything that's been covered in this, please just let me know and I'll do my best to help. Otherwise, I hope it's been good. Thank you.